Welcome everyone. In today's class, we will discuss two final topics of the fundamentals of organometallic chemistry and specifically for their reaction mechanism and type of reaction that we would like to discuss further in later classes. Today we will discuss external attack by ligand and subsequently we will discuss the reductive coupling reaction. So external attack by ligand is the first topic. As you know, organometallic complexes promotes a number of unusual reactions. Without the organometallic complexes, such reaction would have been impossible to happen. For example, if you have simple olefin, you would like to get it attacked by any external nucleophile. Can you do that? The simple answer is most often you cannot. But what if that olefin is attached with a metal complex? Then perhaps you can get a cationic intermediate and where a nucleophile feel encouraged to attack on the olefin. So organometallic intermediate or metal center in particular is promoting such an atmosphere that the olefin, which is otherwise unreactive towards a certain nucleophile, becomes reactive, and therefore a wide variety of reaction can be promoted by utilizing this tactic. Let's look at external attack by ligand. So first of all, as I was trying to tell you, it is an activation of ligand towards attack by external nucleophile. So from an outside source, a nucleophile will attack on the ligand, namely olefin, and that ligand is associated with the metal center. Without association of the metal center, this attack may not be feasible. So let's say you have a metal olefinic intermediate, okay, olefin cationic. So over here you feel that olefin will be cationic in nature, and then an external nucleophile will come and attack to give you the overall product, and that is this metal nucleophile intermediate. If this metal center was not there, simple attack of nucleophile on this olefin would not have been possible in a normal scenario. Of course, there are a variety of reactions that can be of this type. Mostly we will discuss quite a few examples over here and try to say how this metal olefin or metal ligand interaction is helping you to get the nucleophile onto that particular ligand. Okay, an example with the iron complex. Okay, the first example will be the one where you have a iron complex associated with carbon monoxide, so to speak, and this Cp plus, where you have olefin coordinated with it. This is an 18 electron species. Now this is a cationic intermediate. Over here methoxide, for example, will attack and give you iron methoxide complex with a CO and CO to be there with cyclopentadiene ring. So this is one of the clear example of a nucleophilic attack on ethylene, for example, in this case, where methoxide is the nucleophile and you get this alkyl metal alkyl intermediate from there. Okay. Other type of reaction that can be promoted is the metal, you have a metal cyclohexene or benzene complex, for example, metal benzene complex, eta 6 mode of metal benzene complex, which then can be attacked by an external nucleophile. So let's take a look at one of those examples where metal alkyne or let's say metal benzene or metal benzene intermediate, eta 6 benzene intermediate is associated with the metal, and then those metal center is promoting an atmosphere to those benzene ring, eta 6 benzene ring, so that one of the carbon center of the benzene ring now can be attacked by an external nucleophile. Okay, let's try to look at that. So you have a eta 6 benzene and there is a nucleophile associated with it, and over here upon reaction you are going to get a nucleophile getting attached with the with this particular center to give you an eta 5 metal center. Okay, so this is an eta 6 metal center. Overall, now you have eta 5 metal center. A particular example of this type would be the chromium complex. So you have eta 6 chromium tris carbonyl complex. So tertiary butyl lithium, for example, one of the nucleophile which is very reactive intermediate, now overall can give you this product where your tert-butyl is attacking on the benzene ring overall to give you this eta 5 intermediate and this chromium CO3 complex. Of course, as you can see in these cases, in both the prototype and the example chromium complex we tried to discuss, both these cases we are seeing that aromaticity is getting lost, and in the form, of course, that is going to be one of the very difficult process. One can imagine that losing the aromaticity is going to be very difficult. So perhaps this nucleophilic attack will not be feasible. Indeed, what happens in these cases is you need something like carbon monoxide to withdraw the ligand, withdraw the negative charge, so that overall these that anionic intermediate that is getting generated over there can be stabilized through the metal center. So it is essential, or it is important to have the carbonyl to stabilize the intermediate. Therefore, the nucleophilic attack can be possible. So overall, what we have seen so far in the iron complex, the olefin is feeling encouraged to be attacked by an external nucleophile such as methoxide. In this case, we have seen tert-butyl lithium is attacking the eta 6 benzene, which is coordinated with the metal center such as chromium tris carbonyl species. Since it's a tris carbonyl species, such an attack become feasible. Losing aromaticity still is possible because the generated intermediate will be then stabilized by these 3 carbonyl interspecies. Okay, let's try to look at related some other example. Of course, we are familiar with the pi allyl chemistry, right? So in the last case, we have seen that attack is happening by an external ligand. We can have, let's say, this allyl halide or any allyl intermediate. Overall, we can get this organometallic intermediate where we have this allyl species generated from there. Now from there, if a nucleophile is attacking, we are going to get ln m plus this nucleophile over here, right? So this is also an example of a nucleophilic attack by an external attack by a ligand. Here, any nucleophile can attack on this intermediate metal or organometallic intermediate, where we clearly see that the allyl halide, for example, is the starting material. On that, this intermediate that involved is the pi allyl intermediate, where pi allyl now is getting encouraged to be attacked by a nucleophile from outside, and we see that overall this is a allylic nucleophilic intermediate that is getting generated. This sort of reaction can also be applicable for even bigger molecules such as natural product synthesis. One might will be familiar with the name vancomycin as a vancomycin is one of the last resort for this antibiotic business, and this first synthesis of the vancomycin was done by this technique. We'll just give you an example where the main key step or the key step involves the attack by the external ligand. So it's a ruthenium complex. For example, let me draw the complex first. So this is the complex. You have a huge attachment. I'm not going to draw all of it because it is really gigantic attachment. And overall, you have methoxide over there, hydroxy over there, hydroxy over there, right? And the product that one is going to get from these complexes is the overall this hydroxy is going to attack at this carbon center, to give you the final product. As I was saying, this is a gigantic molecule. I am not going to draw it. So, you have this final product in the form of OMe and hydroxo over here, right. But in this complex, of course, if you are looking at this reaction, this is the starting material where you have a halobenzene and in one hand, and you have the phenol in the other hand. So, you have two counterparts. In one part you have the halobenzene, and in another part you have the nucleophile, that is hydroxy. You want to replace the halogen with this hydroxy group. In general, such a reaction is not going to happen. If you have a chlorobenzene, for example, and if you have a phenol, if you want to displace the chloro with the phenolic oxygen, you are not going to get this reaction that very easily without the help of organometallic intermediate or organometallic species. Now, in this particular case, what scientist has done it, that chlorobenzene containing ring, they have interacted it with a metal center. Therefore, this benzene ring feels encouraged, or benzene ring can be then attacked by an external nucleophile. In this case, it is an internal one, because you have a intramolecular setting, and overall then if you look back again with this complex, it is a ruthenium complex, cationic complex you generate with a PF6 counter anion over there. So, this species, without the ruthenium, this reaction does not occur. With CP ruthenium and PF6 minus, once you form a complex, or in situ you form a complex, and then this hydroxy group can attack or at this ring, this hydroxy group can attack on this ring to give you the overall product. And this is the synthesis of one of the key steps of early vancomycin synthesis. Okay. So, what we have learned so far in this part, external attack by ligand is one of the very powerful technique, but it has to be utilized quite efficiently for the reaction purpose. It is even possible to synthesize a variety of natural products by utilizing this technique, where organometallic intermediate will make a positive charge or partial positive charge on the electrophile, or so to speak, let us say on olefin or on the benzene ring, where eta 6 benzene mode it was attached with the metal center, and therefore, those partial positive charge which is created by the metal center now can be utilized by an external or a intramolecular substrate to give you the very give you very interesting example of such category of the reactions. Okay. So, in this topic, what we have learned is a variety of reaction can be promoted by an external nucleophile, but this reaction needs the help of the metal center. Without the metal center, such a reaction may not be, or most likely will not be possible. The next topic we will see the reductive coupling reaction, where we will try to see the alkyne and olefin putting hands together and to form a gigantic molecule, or a heterocycle or a metallocycle reaction, which can be of real great example for the organometallic chemistry. So, next topic we are going to see is reductive coupling. This is almost the last topic going to be on this series of reactions, where we were discussing various techniques to do the reaction, right, the reaction mechanism, so to speak. It is a oxidative cyclization process. Now, this is again one of the other type of reaction which sometime we see. Of course, we have a d electrons present in this metal center, ligand metal center, alkynyl and alkyne. We take, let us say for example, alkyne and olefin both. What we have is metal alkyne interaction as well as metal olefin interaction. Of course, let us say this is N plus oxidation state over here. Subsequently, what we can happen, what we can see is this metal alkyne can interact with the metal center in a 3-membered fashion, and can give you this bond, where one of the alkyne is getting bond is inserted into there, and of course, you have still the olefin interacting with it. So, beta migratory insertion occurs further with this. So, from this intermediate where you have this double bond and 2 double bond with coordination with the metal center, then you have metal N plus 2 oxidation state. Of course, this will be also N plus 2 oxidation state, N plus 2 oxidation state. Overall, you have an intermediate which is 5 membered in nature, and therefore, from there on we can get the reductive elimination to get a variety of product. Okay, so this is an example of reductive coupling where oxidative cyclization is occurring. We have a metal center, and metal center is having an alkyne and olefin interaction in their first step. Alkyne get associated with the metal center further to give a 3-centered or three-membered metallocycle intermediate with the olefinic double bond. That intermediate is going to be very much reactive, and then overall that 3-membered metallocycle intermediate will react with the olefin and thereby forming a and final 5-membered metallocyclic intermediate to give you the product. And of course, from this 5-membered metallocyclic intermediate you can react with different, let us say, halogen, let us say bromine, chlorine, iodine, to give the carbon halogen bond formation at those metal carbon centers. Okay. Let us take a look at another example of this category, and which is by Nigisi actually, and here we have an alkyne intramolecular substrate. In this case, alkyne is there. So, it is an intramolecular alkyne and olefin together. Of course, you can have over here, let us say you can have X over here, you can have NBN, N-benzyl, oxygen over here, or some other even carbon you can have. Overall, what you can have is a Cp2 zirconium species reacting with them to give, this is a D2 species of course, and first you form an intermediate where zirconium is associated with this. This is trimethyl also known as TMS, usually we write down as, and then from there on we can get an intermediate where, let us say, this X comes into the picture and then olefin attaches with it to give you the further intermediate. So, overall what we are having is an alkyne and olefin together attached. So, intramolecular substrate, this alkyne is interacting with the zirconium cyclopentadiene zirconium species to give you a 3-membered metallocycle intermediate. From there on this oxidative cyclization happens, and overall subsequently you will get a, of course Cp2 is over there, cyclopentadiene zirconium, and you get an intermediate where these 2 bond formation happens, and then metal gets in attached with over there, and 5-membered cycle, 5-membered this cyclic intermediate formation happens, and then olefin or TMS member is present. So, what is happening over here is metal is interacting over there and forming a 3-membered intermediate, and these 2 carbon center then subsequently form bond, and of course it is between these 2 center, and it goes on to form a 5-membered metallocycle there, and a further 5-membered metallocycle, 5-membered cycle there, and 5-membered metallocycle over there. If you want, you can treat it with X2, both the X can join over there to give you the final product. So, in today's class we have learned so far that external attack by ligand is a feasible process where metal prefers or metal encourages the external ligand to attack on the unsaturated part of the molecule or olefin specifically, and subsequently we have seen oxidative cyclization reaction where of course by reductive coupling, where we have seen that alkyne and olefin can be stitched together to give you the 5-membered metallocycle, or even the 2 different 5-membered ring depending on the nature of the external substrate. Now, these are different type of reaction so far we have discussed. We have seen, starting from the very beginning, we have seen oxidative addition, reductive elimination, subsequently alpha abstraction, alpha elimination, beta abstraction, beta elimination, and all different type of migratory insertion we have seen, and very recently as well as we have seen 4-centered reaction mechanism, followed by these 2+2 reaction, external attack by ligand, and very recently we have seen the oxidative cyclization processes. So, these are all these methods are going to be very useful if we are going to apply these methods for synthetic setup. If we are going to see a reaction mechanism, it is going to be very useful technique to use. In a moment, in the next class, we will be discussing how these very fundamental processes are almost invariably there in every reaction. All these fundamental steps that we have discussed so far will be utilized for so called different name reaction or more famous reaction which we have seen all over in the organometallic chemistry. We will take all these understanding into effect for discussing those simple reactions. In the next class specifically, we will be discussing the hydrogenation reactions and how these hydrogenation reactions are utilizing this basic principle to come up with the hydrogenation as we see of different unsaturated molecules. Okay. Till then, we will see you soon, keep studying, and next class will be on the hydrogenation. Thank you very much.